So, yeah, the process, step 1, 2, and 3 we did in chapter 5. You've got to find the equation of motion, then using the mechanical impedance matrix, find the natural frequencies, and then you find the mode shape. Okay, straightforward. Step 4 is you've got to find the modal mass. I've written the stiffness matrices here, but you don't need to worry too much about the stiffness matrix. There is a process you can go through to find the stiffness matrix using the same process as the modal mass. Okay, and basically it allows you to check your value for phi, but we're not going to worry too much about that. UV scale to unit modal mass, finding the modal matrix. Okay. You deal with the applied force, you solve the equations, and you convert them back to displacements. So like I said, we'll do an example. And this is our system. We've got a 2 degree of freedom system here. Okay. We've got K, 3K, and K in here. Our masses are M and 2M. Okay. X1 and X2 represent our displacements for this mass and this mass respectively. And there's some forcing functions being applied, F1 and F2. And for this system, okay, we're going to say that F2 is 0. There's no force being applied to this mass. But with this mass, we've got some constant times by time. It's a ramp forcing function, basically. As time increases, the forces being applied to this one will increase. And we're assuming initial rest conditions. The displacement of x1 and x2 at time equals 0 is 0, and the velocity of x1 and x2 at time equals 0 will also be 0. So initial rest conditions. And obviously, the question says, what is the response of the system? So we need to find values for x1 and x2. So, step 1, quick method, we can find the equation of motion. Okay, so like we did last week, okay, you can use the quick method and you can plug, develop these matrices to give us our equations of motion. Okay, for the mass matrix, you take the diagonals and they're just basically the sum of your masses. Okay, for the stiffness matrices, on the diagonal, you take the springs that are connecting each mass to ground or to another mass, you add them up and you plug them in. And for the off diagonals, you take the masses that are connecting the masses to the springs that are connecting the masses to each other, you take the sum of them and then you put a minus sign in front of it and they become those terms there. Okay, so there's your mass and stiffness matrices, displacement, acceleration, and obviously to find the natural frequencies, we assume that the system is undriven, it's free oscillation. And you can apply the substitution that we did last week and stuff, go through the process, but if you're aware of what that substitution is, you can jump straight from this to this. Basically, you take this term and you subtract omega squared times by these terms. So you get 4k minus m omega squared. Down here we've got 4k minus 2m omega squared. And then obviously these terms don't change because these terms are 0. We take the determinant of that matrix. Okay. So obviously the determinant is going to be this term times by this term, minus this term times by this term. So there's those two terms there, okay? Minus 9k squared. Obviously here we've got, 4k times by 4k is going to be 16k squared. Minus 9k squared gives us our 7k squared term, okay? We've got 4k times by m omega, and then we've got 8k, so 4 plus 8 is 12, giving you this term. And obviously those two terms multiplied together, you're going to get 2m squared omega to the power 4. This is a quadratic equation in terms of omega squared. We can use the quadratic formula to solve it. So if we go through that process. So there's our minus b plus or minus b squared minus 4ac. Okay. 4 times 7 is 28, times by 2 is 56. 144 minus 56 is 88. The square root of 88 is 9.381. So we get 12 plus or minus 9.381 over 4. And obviously we've got an m. Okay, this k squared m squared is going to come out as mk. The m's will cancel. You end up with k upon m here. So obviously you've got our two values here. 12 minus 9.381 is 0.655. You square root it, you get 0.809. Obviously don't forget your root k upon m here. And if you add them together, 12 plus 9.3 and 1 divided by 4 gives us 5.356. Square root it, you get 2.312 root k upon n. So there's our two natural frequencies, and then you can go through the process to solve for our mode shapes. So the first one, we plug it in, okay, the m's cancel, the k's will also disappear, okay, and you end up with, basically, this is our first mode shape, 1 and 1.115. Okay. You can repeat the process for the second mode. So we plug in omega 2 into our equation, and again go through solving for R2, and we end up with our second mode shape, 1 and minus 0.448.